Hello, this is a list of new nodes which we are going to discover along this lesson. This lesson is completely dedicated to work with the orientations by the quaternion. Let's get started. Since we are going to be working with orientation, I've prepared and advanced this simple geometry that looks like a 3D axis. With this it will be easy for us to identify around which axis the rotation will be. Okay, let's jump into it. I just created a subnet to hide the nodes that are used to build this geometry. Let's go on. Now let's create a grid, then copy this geometry to each point of the grid. Select points just to remove geometry but keep the points. Now let's copy our geometry to these points. That's it, now let's create an attribute VOP. Call it orient setup, then dive into it. Okay, now let's create a bind export node just to create a new attribute. We name it orient. The attribute type must be a 4 floats or so-called vector 4. The copy to points node knows how to handle the orient attribute. Now let's create a quaternion node. This node takes an angle and an axis and constructs the quaternion representing the rotation about that axis. In simple words, quaternion is a 4-dimensional vector that describes a rotation in 3D space. Okay, let's see what it looks like in practice. Connect the quaternion to the bind export. Look, this is the axis around which the rotation should be. In this case, it is an x-axis. The angle is an amount of rotation around a given axis. Now let's tweak an angle. As you can see, they all rotate around the x-axis. Now let's set a z-axis and rotate again. Here we go, now they all rotate around the z-axis. By default, the angle is measured in radians. In case you want to work with degrees, there is a node that converts degrees to radians. This operator converts degrees to radians. Take a look, now the angle is measured in degrees. You can also do opposite. This operator converts degrees to radians. Let's delete both, we don't need them anymore. Now I want to randomize the axis around which the rotation occurs. Plug in the PT num. Select the 3D vector. Then plug to the axis. Now let's tweak the angle and see what it looks like. As you can see, they all have a random rotation axis. Now let's keep these random orientations, then try to rotate them around the local axis. For that we will create a quaternion multiply node. This operator performs a quaternion multiplication with its 2 inputs. We also need one more quaternion. Plug both quaternions to the multiplier. The output goes to the bind node. Look, now they are all rotating around the local x-axis. Now let's change the rotation axis. Instead of the x, let's set the z. Here we go, they are all rotating around the local z-axis. Now I want to do the same thing in a different way. First, let's select all these nodes except the bind export and delete them. Now let's create a Euler to quaternion node. This operator builds a quaternion with the given Euler rotation. The input has to be in radians. Connect to the bind node. Look, now we can rotate them around any axis. Okay, now let's randomize their initial orientation. We also need a quaternion multiply node. As well as let's create a one more Euler to quaternion. Multiply each other and plug to the bind export. Now let's test our setup. As you can see, they are all rotating around local X. Let's try also around the Z-axis. Here we go, we did the same in a different way. Now I want to show you some simple ways to randomize the orientation for each one. Let's delete all this again. Then create a turbulent noise. Plug to it P. Select original Perlin noise. As well as we need a 3D noise. Now let's create a vector to quaternion. This node converts the vector to quaternion. Let's plug in the noise. The quaternion goes to the bind export. Now let's tweak noise amplitude and see what it looks like. That's it. With the amplitude of the noise, we can control the amount of rotation. Of course you can control the noise frequency, offset, and so on. Okay, now I want to show you a short and simple way to generate random orientations. Let's create a random node. Plug to it the PT_num. Then choose a 4-dimensional output. Plug to the bind export. Here we go, we have random orientation for each of them. Now I want to do something more complex with quaternions and in the process show you another important node related to quaternions. Let's delete this node. Then create a quaternion node. Plug it to the bind export. I want to dry the angle by time. Let's play the animation and see what we get. Toggle the animation in real time. Let's increase the rotation speed by multiplying the time by some value. Now the rotation speed is good for me. Let's create another quaternion node. For this one we will keep the default properties. Let's plug it to the bind export and see what we get. Okay, let's return the old connection. Now I want to introduce you to the quaternion distance node. This operator computes the angular distance between two quaternions, measured in radians. Let's connect both quaternions to it to measure the angular distance. Now I want to export the angular distance as a new attribute and see what it looks like. I will name it quat_dist. Now let's open the geometry spreadsheet. Hide all attributes, then display only quat_dist. Let's run the animation and observe how this attribute changes. Look, between them the angular distance increases and then decreases. The transition moment is a semicircle. The semicircle in radians measured 3.14. In degrees it will be 180. Actually we can convert the radians to degrees. Let's run animation and check the quat_dist attribute. Here we go, the angular distance increases to 180 degrees, then starts to decrease. Excellent, we can move on. Now I propose to use the angular distance to drive p-scale. First, let's fit the range of angular distance. The source range must be from 0 to 180. The destination range will be from 0.25 to 1.5. Now let's create a p-scale attribute and drive with this modified angular distance. Great, let's run the animation and see how it looks. It doesn't look good so far. I propose to shift the p-scale with some interesting mask. I'm going to use the relative to bounding box information. Give it all the inputs it needs. Now let's create a getVector component and extract the relative to bounding box information along X. Now let's add this mask to the time that drives the rotation. Before adding, let's add a fit range node to get an additional control. Here we go, now they rotate and scale unevenly. Of course we always can control the mask range. Let's put a 1.5 for now. I also want to increase the global rotation speed. Let's multiply by 4. Okay, looks good, we can move on. Now let's create a color and try to manipulate it with an angular distance. We need a fit range node, let's create it. Then plug the angular distance to it. Put a 180 here. Now let's create any color, then start to modify it. To edit this color I'm gonna use the hue shift. Plug to it the color. The output goes to the CD port. Let's make one the shift amplitude. Now I want to drive the shift amplitude with angular distance. Connect the angular distance to the shift amplitude. Here we go, we got a variety of colors, it will look more interesting during animation. Let's play the animation and see what it looks like. Looks nice. Of course we can reduce the shift amplitude and achieve less color variation. Now I want to change the rotation axis and see how it looks. Let's set a y-axis. Not bad too, let's also try around the z-axis. Looks more interesting, but I want to inverse the rotation, for that we can use a quaternion invert node. This node outputs the inverse of the input quaternion. This will rotate vectors in the opposite direction. That's it, now they rotate in the opposite direction. Okay, let's go on, now I want to add some randomization during the rotation. For that I will create a random node. Plug to it the pt-num. Create a multiply node. Then connect to the time. Let's also create a fit range node, then plug to it the random values. Put a 0.75 for destination min. Then multiply these random values by time. Now let's run the animation. As you can see, we randomize the rotation order. Let's reduce the impact of randomization by increasing the destination value. Looks cool, but I want to decrease the impact of randomization even more. Let's put a 0.9 and do a final look. Looks great, let's go on, I want to do final correction. This time I want to increase the shift amplitude. Cool, I like it, now I propose to stop at this and start something new, in the process of studying other nodes related to the quaternion. Okay, this time I'll be using this simple torus, which I've pre-assigned a color to make the rotation around the y-axis more noticeable. Well, let's create an attribute VOP. Connect the geometry to it, then dive inside. Let's create a rotate by quaternion. This node rotates the provided vector by the quaternion. Since the input is treated as a vector, it is a rotation around the origin. The quaternion should be normalized. To rotate by quaternion we can use Euler to quaternion. We will rotate the position vector. Plug the output vector to the P. Look, we can now rotate geometry around any axis using a quaternion without an orient attribute. Since the center of torus matches with the origin, everything is perfect. Let's jump at the object level and move the torus away from the origin.